So welcome to the first part of our lesson on managing the Java thread lifecycle. In this lesson, we'll understand the Java thread lifecycle and examine its various states. The primary focus of this lesson will be on starting and stopping Java threads. We'll begin by giving an overview of the states in the Java thread lifecycle. A Java thread is a complex entity that interacts with many other entities. The lifecycle of a thread must therefore be managed very carefully. A thread transitions through various states based on operations that are performed by a Java program. Two of the most fundamental parts of a Java thread's lifecycle involve starting and stopping it. You don't need to understand all the details of Java thread internals in order to be able to program them effectively. However, your reputation and value as a so-called full-stack developer will increase if you learn how threads work internally. We'll now give an overview of the state machine for Java threads. The thread states are described in the URL at the bottom of this document. As you can see, there's about 7 different states in all. This URL provides an overview of the state machine diagram that's very similar to the one that's shown on this screen. You begin by creating a new thread object. If you say new my thread or new GCD thread or new thread, that will go ahead and create a new object, and it will also transition the state machine into the new state. At this point, you can say start on your new thread, and this will go ahead and launch the thread, start all the various pieces in motion. After start is called, various things happen. The underlying operating system and virtual machine will create various resources to run the thread, such as a stack, various registers, other internal state, and it will also set the state of the state machine for the thread to the runnable state. At this point, the Java and Android Linux thread scheduler control what happens, since there may be multiple threads waiting for their chance to run. So a thread, once it's started, doesn't immediately begin to run. It will actually run when the scheduler decides to select it to run. Once the scheduler selects it to run, it transitions into the running state. And then the underlying Java execution environment, the Java virtual machine, Dalvik, Art, etc., will then invoke the thread's run hook method, which is actually where the code resides that's written by an application developer. At various points, the thread, while it's running, may call methods that cause it to wait for a period of time. Things like the sleep method, the wait with timeout method, the join with timeout method, and so on. And when this happens, the underlying scheduler transitions the thread and its state into the timed waiting state. Once things time out, once the timeout elapses or the operation completes, then the underlying system will transition from the wait time elapsed, timed wait state, back to the runnable state. Note, however, that the thread does not start to run immediately at this point. It's simply ready to run. The scheduler will then select it when it's time, and it will set the state to the running state, and then it will go ahead and call back on the run hook method, keeping in mind that where the run hook method will take up will be wherever it left off before, when it went into the timed waiting state. At some later point, the thread may end up blocking, for example, when it tries to access a guarded resource, such as a monitor lock, that's currently in use by another thread. When this happens, the thread is transitioned to the blocked state, where it will pause and wait until whatever thread is owning the current blocked resource releases it, in which case the thread will be able to start running again. So once the resource is acquired, then the thread is no longer blocked, and the transition of the state machine will go from blocked into runnable. Once again, of course, note it doesn't start running immediately. That's up to the job of the scheduler to detect when it needs to be able to run. It then transitions to the running state, and once again, the run hook method is called back. At this point, let's assume that the run hook method or some method called by the run hook method will end up calling wait on the monitor object. So it'll use the monitor condition to call wait. Note, of course, that the monitor lock must have first been acquired in order to call the wait method, otherwise you'll get an invalid state exception. In this case, once the wait is called, we then transition to the waiting state Notice, by the way, this is done for the non-timed version of wait. So we're in the waiting state, and then at some point later, some other thread will call notify or notify all, and that will cause this thread to be able to wake up, go back to the runnable state, and then at some point when the scheduler selects it to run, it will go back to running, and then its run hook method can be called back once again, or resume, pick up, resume running where it left off before when it was waiting. The run method can either exit normally by falling off the end of run, or an unhandled exception may occur. In either case, the run method has been exited, and at that point, the thread is going to be moved to the terminated state. At this point, then, the underlying Java execution environment can reclaim any of the resources that the thread had allocated, such as its stack and other registers and so on, and the thread resources will be able to be reused by some other part of the system, such as another thread that may be started at some later point in time. So that essentially gives you an overview of part one of our lesson on managing the Java thread lifecycle. So we're now about to talk about the second part of the lesson on managing the Java thread lifecycle. Earlier we talked about the thread lifecycle and talked about its various states. Now we're going to talk about the steps involved in starting a Java thread. And it turns out, because of the complexity and sophistication of threads, that there's some interesting design and implementation issues associated with starting a thread. And when you start a thread, the ultimate consequence of this is it'll lead to the execution of its run hook method when it's runnable, when it's able to run, and the thread scheduler decides it can run. A bunch of things happen in various layers of the Java platform or the Android platform when someone starts a Java thread. So there are Java class libraries that are involved, the Java execution environment is involved, the operating system, native libraries, there's a whole bunch of different things that are involved in doing this. Now, I'm about to walk you through a piece of some stuff from a version of Android. Be aware that different versions of Android and different versions of Java platforms may implement these layers somewhat differently, although the key levels of abstraction are very similar, and the basic steps are going to be the same. And I'll really emphasize the most important steps when we get to them. If you can take a look here, and you can get access to all the source code that goes along to what we're discussing. The other thing to remember as we go through this, and you'll see there's a lot of steps, creating and starting a new thread consumes a non-trivial amount of resources. So use threads judiciously. And a good rule of thumb is make sure you spawn threads for things that run a lot longer than it takes to start a thread. Right? So if you're going to start a thread and it's going to add two numbers together and be done, it probably takes many orders of magnitude longer to create the thread than it did just to call, add the two numbers together in the current thread. On the other hand, if you're going to download a giant file, or you're going to compute some long-running computation, or you're going to do something on Android that takes longer than the application not responding exception will let you get away with, then it makes sense to use a thread. Or it may make sense. You have to decide. So typically everything starts when your application says start on the thread object, so that's up here at the application layer. Then that start call, of course, is actually what's implemented by the threads.start method that comes from a class in the class library. You can go take a look at the source code. If you're looking at Android, this will show you the source code for that class. On this version of Android, that ends up calling something called a VM thread, which is a native method, which means it's implemented in C or C++. That ends up calling down into something inside the Android virtual machine, which is called Dalvik. There's still vestiges of it residing in Android, even though they've moved on to something called Art for a lot of the stuff that they do. So that's a Java native interface method that's written in C or C++. That calls down into something inside of the underlying virtual machine, DVM, that stands for Dalvik Virtual Machine, create interp thread. So we're still in the execution environment layer, but we're a little bit lower down in that. We're in the VM part of it. That method, which is written in C, now calls to a pthread create method, which comes out of the native libraries. So now we're talking about native libraries that are written in C that are part of the Android platform, the native libraries. This would be libc. And this is actually just a standard pthreads. Pthreads is a common C interface for accessing threads on Unix operating systems, including Linux and Android Linux. And that will go ahead and create a thread. And notice we have this thing called interp thread start. This is actually a pointer to a C function. And that'll be important in a second. And this pointer to a C function is the entry point that allows us to transition between C code. Notice we're in C code right now. We started out by making a Java start call on Java code. We quickly found ourselves in the VM implementation, which is written in C, or C++. And now we're down into pthread create. This is provided by the standard libraries on Linux. And now we've got interp thread start. And now we're going to transition inside the Android Linux kernel. And I can't even begin to tell you how much code goes on here, right? This is where the real heavy lifting takes place. I'm not going to walk you through that code. It would be mind-numbing. But if you really want to hurt yourself or be enthralled and entranced by really cool low-level stuff, you can actually get access to the Android source code and read through it, and the Android Linux source code. The key point is that pthread create, in conjunction with the Android Linux kernel, will create a runtime thread stack. This, of course, is where methods will be called and execute. And this interp thread start function that was passed here to pthread create is actually the initial entry point into this stack. So that's the function that gets called back. That's a C function that gets called back. That function will in turn call dvm call method, passing in the object for which this thing is run, here, the self thread object, and the run hook method. And that will then end up calling back the run hook method. Now we're back in Java land. This is now in Java. This is the run method called back on the original Java object where we called start. So up here we called start, Java code, C 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 code, and then finally we get back to Java code again. So it's a rather long and circuitous route to get from Java code, where start was called, to Java code, where run is called, the run hook method is called. And, whoops, and that's basically it. Those are the steps that are involved in doing all that. Any questions about that? Pretty interesting, right? Number one, you can see that there's almost a dozen methods, and I left out probably another 20 methods that are called in the Linux kernel to actually do the real heavy lifting of making a thread. So whenever you call thread start, think to yourself, do I really have enough to do to warrant all of this overhead? OK, so that's the end of that particular piece. So now we're in the third part of this lesson. And what we're going to do here is talk about various ways to stop Java threads. So up to this point, we've talked about ways to start them. And now we're going to talk about ways to stop them, so the other end of the life cycle. And there's a couple of different ways to stop them. The one we're going to talk about here, or at least begin talking about here, is stopping a thread using a so-called volatile flag. And the idea of this flag is to tell this thread to stop. So it's a way of disturbing the thread. So please do disturb. So there's a variety of reasons why you might want to stop a thread. Why would you want to stop a thread? Well, one reason you might want to stop a thread is that the user may get bored or tired waiting for something to happen, right? So you might be doing a long-running computation. You might be searching the web or doing something, and you're like, this is taking way too long. I don't want to wait here all day. I'm going to stop. So that would be one thing. You want to cancel something that's taking too long to run. Another reason, which is a more Android-centric reason, is that an activity is destroyed, stopped, or paused because the user does a runtime configuration change or presses the back button. So in that case, you may, depending on your program design, want to stop the existing computation because it's about to disappear, and therefore there's no sense keeping it running around because its output will never be used for anything. Now, as we saw when we looked at the GCD concurrent app, I had an intentional design flaw where it leaked a thread when an orientation change occurred. So when you change the orientation, the thread was not shut down. It kept running, but we never got the output of it for anything. So it was just wasting resources unnecessarily. But the broader reason is because you've destroyed an activity or you've stopped it or something. Another reason is you may be doing some kind of speculative computation, and once somebody knows the answer, you want to tell everybody else to stop. So it turns out that there's a method in the Java executor service, which we'll look at later, called invoke any. And invoke any will take a list of callables, or runnables, let's say runnables for the sake of discussion, and it goes ahead and it starts running them all. And whichever one gets the answer first, then it goes ahead and cancels everybody else. So you could imagine doing this for some kind of a, gang scheduling or work where you want to go out and search for something, like go search a bunch of different files to find some kind of key or some kind of string. And whoever gets it first, you want to kill everybody else off because you've got the answer. Another good example would be if you're playing some kind of chess where you have AI program and you want to be able to, evaluate a bunch of different paths through a search tree. As soon as you find the winning move, you want to stop everybody else and return the result. Now, it turns out, interestingly enough, that stopping Java threads is surprisingly hard. And I like to call this the sorcerer's apprentice problem. If you've never seen the classic Disney movie Fantasia, you should watch it. And I think if we're still lucky, if the intellectual property police haven't come along and gotten rid of it, I think if you go to this link, you can find out about Fantasia. In Fantasia, it's a great animated film made a long, long time ago, but it's still cool. It's back when they used to, draw every frame by hand, so you can imagine how long it took. There's a classic scene where Mickey Mouse is basically an apprentice to a wizard, the sorcerer. So he's kind of like a grad student, right? And so his master, his wizard master, has said, I want you to take this bucket of water and, basically fill up a tub from a well. Well, Mickey, being a clever but not necessarily experienced apprentice, decides he will enchant a bunch of brooms to do the work for him. Well, if you watch the clip, you find out that the brooms start to multiply and he takes an axe to them, but they keep coming and keep coming. And so the point of the whole thing is that setting things in motion is sometimes harder than stopping them, right? And that's really true with threads. So I call that the sorcerer's apprentice problem. And it turns out that there's no safe way to stop a Java thread involuntarily. You cannot tell a thread to stop. You have to request it to stop. And if you read this particular link, it'll explain to you why that's the case. There's a bunch of reasons. It has to do with the fact that the stop method is inherently unsafe. What that means is that it means several things. It means that all the monitors that a thread holds are automatically unlocked as the shutdown thread exception propagates up the runtime stack. And as a consequence of this, you'll have any objects that were protected by those monitors left in some unprotected and inconsistent state. So calling stop, if your implementation even supports it, most these days don't, but if it even does, it's just a bad idea to call stop. It's deprecated. It's not guaranteed to work. It's not guaranteed to be implemented, and if it's implemented, it'll probably leave your program in some horrible inconsistent state. So that's a bad thing. So instead, you have to set your programs up so that long-running computations or long-running operations that take place in a thread are prepared to stop voluntarily. And we'll see there's a bunch of different ways to do that, but here's one example. So you have a run method, and you have some kind of check. While we haven't been shut down, check to see if the thread should stop, and if it should stop, stop it. And you have to voluntarily do that. There's two different ways to stop a thread voluntarily. One way, which we're going to focus on here, this may spill over till next time, is to use the so-called volatile flag. And we'll see how that works. You just mark something as being volatile, and we've seen that in programming assignments. And the other thing is to use a Java thread interrupt request. And that's another way to do things. And they have pros and cons, of course. So let's talk briefly about stopping Java threads with a volatile flag. So here's how to do this if you want to. This is an example, but it's emblematic of this type of approach. So what we've got here is we've got a class, and its run method is going to do some long-running operation. And what we're going to do is we're going to add a volatile flag, which will initially set to false, called m_is_stopped. So the way this is going to work, of course, is that as long as that is false, as long as the m_is_stopped is false, we're going to keep running. And if you recall, when we talked about volatile earlier, that ensures that changes to a variable are consistent and visible to other threads atomically. So when you read and write to a volatile, it propagates to all the other threads right away. It doesn't wait around in a cache. So we're going to add a stop me method. It could be called something else, whatever we want to call it. It could be called stop. Actually, it couldn't be called stop because there's already a stop method. I wouldn't call it stop, let me put it that way. And so this will set this flag to true, which will mean that this loop will then stop because it will have checked that it was stopped. And then, of course, once we've been stopped, it's up to us to get out of the run method as quickly as possible because we've been told to stop. We need to now shut ourselves down in a timely manner. So this solution is very lightweight. It requires no support from the underlying virtual machine, the underlying execution environment. It just requires the Java memory model to be implemented correctly with respect to the semantics of volatile. You set the variable, somebody else checks it, boom, you're done. Pretty straightforward. So it's very lightweight. However, it's not transparently integrated into the Java execution environment. And what that means is if your thread is blocked on a long-running operation like a read of some kind, or waiting on a semaphore, or waiting on a lock, or whatever it's doing, if that's a long-running, long-blocking operation, in other words, it's stuck, then this approach won't work because setting a Boolean flag doesn't do you, a volatile Boolean flag does you no good if your thread is blocked on something that doesn't have the faintest idea about your Boolean flag. So it turns out that we're not going to be able to use this for everything we need to be able to do. All right, so that's the end of that discussion. And I think we have a very short time left.